Hi everyone. Today we're hosting Dr. Priscila Pessi from the Stockholm University. So a very brief biography. She received her PhD from the Universidad Nacional de La Plata, and she has very recently completed her first postdoc at the Stockholm University. She also won an studentship internship at ISO Chile. And right now she's transitioning between jobs, and she's very soon is going to move to Poland for her second postdoc. And her research is mostly focused on the hydrogen-rich supernova, and she's part of the both of the galactic and time domain working groups within WST. And some of her collaborations are as following. So she's been part of the public ESO spectroscopic survey and part of ZTF, and she's also plenty active at the LSST's transients and variables science collaboration. So thank you very much for joining our meeting today and accepting our invitation. We're very much looking forward to hearing from you, and the floor is yours. Please go ahead.
Thank you. Thank you very much for inviting me. It's nice to be here. Well, especially thanks Fateme because she was the one making the invitation, but also thank you, Julia. So today we'll be talking about hydrogen-rich ambiguous transients and how WST can contribute to understand them. I will be focusing on one particular object, but I will try to keep the topic very broad. And especially what I want to stress is how maybe WST in the future or any other spectroscopic survey can contribute to better understand this type of events. And when I say ambiguous transient, it's transient that we don't really understand the physics of. When we see a transient event, our first goal is to try to understand what is powering them, what is happening physically to produce them. So typically, a good scenario nowadays is to have a photometric discovery of a transient. Of course, in the latest years, we have been having multi-messenger discoveries, but in most cases, most surveys nowadays are photometric, so we mainly have photometric discoveries. And then if we are lucky, we will have a spectroscopic observations and we will obtain a spectrum, and then we will match this spectrum to known events, and then we'll have a classification, and with this we can propose a physical interpretation of the event that we are looking at. More common scenario these days is to have the photometric discovery and only have photometric follow-up and not have any spectrum at all. Luckily, in the latest years, people have been doing a lot of work in machine learning techniques to be able to provide photometric classification through light curve matching, more or less. So we can have a classification via the light curve, and then we can propose a physical interpretation in this way. However, as I say, there is a growing number of events that are very difficult to identify the physics of. So we do have photometric discovery, and then we may have even spectra and photometric follow-up both. So this will be the ideal scenario for any transient to have both. If we have more, is best. But then the spectra and the light curve don't. It's not that don't really match. It's the opposite. They match too many known events and different events, and so then a physical interpretation is complicated. And this is particularly not unusual when you have interaction. So when the transient is hidden behind dust and gas, you can have spectral lines that show that are mainly hydrogen lines, and particularly narrow hydrogen lines in the spectrum. And then you have very long-lived and bumpy light curves. And what you're seeing really is the interaction and not really the power mechanism of the event. So trying to understand the physics is very complicated because the main thing you're seeing is the interaction. And there are three types of events that show this, mainly supernova. That supernova are my main field of study. In particular, core collapse explosions when they are enshrouded in a hydrogen-rich circumstellar material that was produced by the progenitor star through different mass loss mechanisms. When the star explodes, then the supernova will interact with this circumstellar material, and then we will only see the ionized CSM through these narrow hydrogen spectral lines. And these are classified as type 2N supernova, and particularly they are, in many cases, very luminous, and in many cases, long-lived, and in many cases, we just see the interaction, and we cannot see the actual supernova that is behind this CSM. We can also have AGN, and AGN, we have this unified model where a supermassive black hole is accreting material, and the differences between the AGNs that we see are just produced by the line of sight. And we have different line of sights where we will mainly see narrow hydrogen emission lines in the spectra. And the light curves of AGN are also very bumpy and long-lived. And of course, we can also have TDE, which are the disruption of a star by a black hole, and in these cases, it's also possible to see these narrow hydrogen lines and the long-lived bumpy light curves. But all these three events are very different from the physics point of view. So they are produced by different mechanisms and so on. However, the observational features that we see are very similar, so it's very complicated to disentangle them. And here there is an example. So on the left-hand side, we see light curves of different events, supernova, TDE, and it's very complicated just by the light curve to see which is which. And then on the right-hand side, we see spectra. And here we also have, in the spectra, we also have AGN, and it's also complicated to say which one is a supernova, which one is a TDE, and which one is an AGN. And as I said before, I will be focusing on a specific object, which is this one, AT2022 RCE, which is a transient event that occurred in 2022. And we compare its light curve here in orange to supernova 2010 JL and IPTF 13Z and IPTF 14 HLS, and also to the TDEs Assassin 14 LI and SDSS 1115 plus 0544 in blue. And you can see in the absolute magnitude here in the top panel, all these events are quite bright, quite luminous, so they are also quite energetic. And then if we normalize based on the light curve peak, they all show bumpiness and a bit of messy behavior, if you want. When you look at the spectra, you see 22RC in black, and then you have two supernovae that are very similar, showing these narrow hydrogen emission lines. IPTF 14 HLS is the one that is different, spectroscopic-wise. Then we have two TDs, and then we have two AGNs. And in this case, the main features that we see is always these narrow lines. So to focus a bit more on this object and to try to understand it better, we can check the discovery certificate for this event. And we can see that it was discovered in August by Gaia and proposed to be a supernova candidate. And when we look at the stamps obtained by CTF and gathered from the LRC broker, we look at this, and you see in the template a galaxy there in the center, and in the science you see a luminous a point south to the host, and then you say, okay, this looks like a supernova. If the transient would be in the center of the host, then you don't say supernova so quickly, because then at the center of galaxies there are the massive black holes, so then it is likely that it could be an Asian flare or a TD or something like that. But in this case, At this point, there is nothing so suspicious. Um, Luckily, we got spectrum in December 2022. This is already very late, so we don't have any early spectroscopic observations. And based on these narrow hydrogen lines marked in blue, it was classified as a type 2N supernova. However, in 2024, we got another, well, not we, but people, the community got another spectrum and then proposed an AGN for a classification, and mainly based on the presence of forbidden oxygen 3 lines. However, when you look at these lines, they are there, and you can see these lines are both in the late spectrum and in the earlier spectrum. So in this case, you can imagine that both spectra can match type 2N supernova and also AGN. So uh, then we got curious to try to understand what this event really is. Particularly because at the time I was studying superluminous supernova, and I wanted to see why the behavior of this particular event was different than the others. At this point, I was still thinking this was a supernova. So we look at the host, as I said before. When you just look at it at this, there is nothing strange. But if you look deeper into it, and you go to see the legacy survey images, you see a lot more structure. And if you see here in the center panel, we call the host, we say the host is everything that is enclosed by this green ellipse. And then we decided to take this R-band image from the legacy survey and produce these contours based on equal intensity in the pixels. And we see that there are two separate sets of contours that are close. So we can assume in this case that there are two different nuclei for this galaxy. So having two different nucleus for a galaxy is not common. So in these cases, what you would assume is that you have two galaxies that are merging. So in reality, the host of this event is a merging system. And when we see the colorized image here on the left, you can be convinced of that. You see the two very bright nuclei of this host. So you say, okay, this is really two galaxies that are merging. And 2022 RCE happened in the center of the small component of the merging system that we will call galaxy B, where the big component we will call galaxy A. But now, because AT 2022 RCE is at the center of galaxy B, it's not as straightforward to assume this is a supernova. Of course, a supernova is not excluded, but as I said before, because we have a massive black hole at the center of galaxies, then we have to consider a possibility of an AGN or a TDE. Luckily, there was a DESI spectrum. You can see here on the right-hand side, the blue spectrum of galaxy B, way before the transient occurred. So you can see here in days, how many days before the peak of the transient. And then we also got spectra of galaxy A for two different epochs. If we zoom in the different key features, let's say, we see H beta, forbidden oxygen 3, and H alpha for galaxy A and galaxy B. And we see galaxy B has a way more prominent forbidden oxygen 3. This is hinting towards the presence of an AGN. We also have X-ray observation that also hints towards the presence, sorry about that, hints towards the presence of an AGN. So we look at the light curve and the spectra. So on the left-hand side, we have the light curve, and if we see the flux of this event in time, we see that there is no activity for a very long time. And this lack of detection, let's say no detection for a very long time, this could be related to the depth of the surveys. Can also be that nothing was happening. But then we clearly see the burst, right? The transient going off. And when we look at the light curve, we see that its peak is very bright. You can see the the peak marked here as a pink star, so it's more than 20th magnitude, minus 20th magnitude. So this would be considered superluminous supernova, and it's very long-lived and bumpy. And in these cases, you already, because of the bumpiness, you can already hint the interaction there that can be producing these bumps. So when the emission is hitting different different layers of the environment of the gas around the event, they can produce these bumps. And we see on the right-hand side the spectral evolutions. So we have the first spectrum 60 days after peak, or as I say, it's already very late. And then we have spectroscopic observations up to 600 days after peak. And we see the whole spectral evolution is rather not an evolution, let's say. It's quite the same thing all through all the phases. And very narrow hydrogen lines, and then very little other features. So it's very difficult to say here what's happening. As I said before, because galaxy B hints the possibility of an AGN, then we have to consider the possibility of an AGN. And the first thing you do to try and figure out if something is an AGN is to place it in the BPT diagram that compares hydrogen lines to forbidden oxygen 3 and forbidden nitrogen 2 lines. When we place the spectrum, or we place galaxy B on this diagram, we clearly see that it's located in the AGN region, so it's this blue star here. When we place galaxy A, which are these gray rhomboids, here we see it's consistent with a star-forming galaxy. And then all the other points are the transient that are all over the place. So we cannot really say what it is. However, at this point, we have to consider this type of AGN that are classified as changing look AGN. This changing look AGN can be so because the galaxy goes from quiescence to activity, or because it was a given type of AGN that is changing its classification. So to know a bit more about this, we also consider H alpha over H beta ratio, and here on the top panel of this figure. And then we also consider the velocity, the full width half maximum velocity of the H alpha feature. And we see this for AT22RC as black stars. And we compare this with TDEs, supernova, and changing look HGN. TDEs are presented in gray, supernova in colors, and then changing look AGN in pink. And for changing look AGN, it's just the stripe because I couldn't find sample measure in a given way for different epochs. So mainly there are measurements for single epochs and so on. And in the case of H alpha over H beta, the measurements are done in a different way as it has been done for TDEs and supernova. So when we consider the ratio of H alpha over H beta, our event closely follows strongly interacting supernova. But for the full we have maximum velocity is more consistent with changing look AGN. Because of this, and because of galaxy B being consistent with an AGN, and because of observations in radio and X-rays, we conclude that this one object is a changing look AGN. And if you want to know more, please go check the paper. But what I want to stress here is that it was not straightforward to understand what this event is, and also this classification as a changing look AGN can be challenged if we obtain more observations of the host, for example. Or it could have been challenged if we had later observations. However, it's quite faint. It became quite faint at the latest times. Of course, as I said before, I wanted to highlight that this is one event of a class of ambiguous events that are complicated to understand. And so if you go check the paper by Weisman et al. In 2025, they have a huge sample of ambiguous candidates that are complicated to place in a given classification, and this means that their physics is complicated to understand. We are not sure what's happening with them or what is producing them. And they are typically faint in apparent magnitudes, and they are typically very long-lived with very faint tails. And they are also typically badly followed. And this is mainly because different groups that study different events, for example, if you are a group studying a supernova and you see an event that looks like an AGN, you are not going to consider it to be interesting. Or if you are studying AGN and you consider something to be a supernova, you're not going to think this is interesting, and then you will not follow up. And then we end up with a huge number of objects that we don't understand and we don't have a lot of observations of. So this is why I think WST is a great opportunity to better understand this type of transients. Of course, there is a long time until WST is live. However, there are other spectrographs in the world, and there are other opportunities to try to use spectrographs as in a survey mode. And so I think the main advantage of WST is that it's going to be a survey. So we have a lot of photometric survey, but we don't have a lot of spectroscopic surveys. And in this case, we will have a good coverage of the spectral evolution from early to late times, if we have a survey, I mean. And particularly very early and very late time spectra will be key to try to disentangle ambiguous events. Particularly if it is a supernova and we manage to observe late enough, we may be able to see the supernova overcoming the circumstellar material. And so then we could see supernova features. So that will help us understand what's happening. In particular, WST will have a large collecting area. So this will allow us, as I said before, will allow us to see faint targets. So this is really lacking right now to be able to have a big sample of spectra of fainter events. And having low to high resolution is also key, because with low resolution you can guess a class, and some classes are very straightforward, so you don't really need more. But then when you are uncertain, then you can switch to a high resolution spectrum and try to see more features and try to understand better your target of interest. And again, in this case, the other advantage is to have integral field spectrograph that will allow us to get image and then to do a deeper analysis of the hosts. That in cases like this is key, particularly when you want to see, for example, if you have a merging system or not, as it was the case of the transient that I presented here. So as a discussion, I would say we need to look more into these panoramic surveys producing spectra, particularly to study events that lie at the intersection of different classes, as can be supernova, AGN, or TDE, to try to disentangle their features. To me, the key point on the reason why these events are so interesting is because I believe that not understanding what is power in this ambiguous transient means that we don't really understand the physical processes that produce transients, at least not in a deeper level, if you want. WST will be great to reach faint and distant objects as this can be. And as I said before, it will be great to obtain late-time observations. So I really hope WST happens. And then we had to think already and try to already decide or figure out how to produce synergies with additional space and ground-based surveys. There are cases of ambiguous transients that have neutrino associations and so on. So this will also be great to have these multi-messenger observations of this type of events to try to understand them better. So with that, I want to thank you for being here and for listening. And that's it.
Thank you so much for the great talk. I really enjoyed it. Thank you. This was very curious, very nice. Okay, so does anyone have any questions in the audience? Curiosities, comments? I actually have one, like before anyone else starts or like think about questions. So I have a very basic question. What really caught your attention to study this particular object? Because ZTF is a huge database, and then how could you just tell that, oh yeah, like this is something interesting, and we want to look like further into this and analyze stuff? How does it usually happen?
So yeah, in this particular case, so there are already a sample of these ambiguous objects that are difficult to place, and usually you are studying something, and then you see something that doesn't really fit into the characteristics that you know of the thing you are studying. And in this case, I was studying type 2 superluminous supernova, and I was looking at particular features and particular measurements of the sample of hydrogen-rich superluminous supernova, and I saw this one object that show almost no spectral evolution at all, and that show very, very long-lived light curve. So this was quite odd in comparison to the other superluminous supernova type 2 that I had. So I was thinking it was an outlier or an oddball among the type 2 superluminous supernova. However, a lot of people started saying it was an AGN, and then there was an AGN classification, and I was like, okay, maybe it's a contaminant in my superluminous supernova sample. And now I think, for a very long time, I was hoping that it was a supernova, but in the end, we conclude that it's probably a contaminant in the sample.
No, right. This is very interesting. Yeah, right. And the second question that I had for you, like just to know your opinion, how do you see facilities like WST, for example, because we don't know if WST is going to be selected at the end. Um, where do you see facilities like ZTF pairing up with spectroscopic facilities? Because I mean, they're like very different. Like the way that we are like seeing alerts from a photometric perspective is very different from what we are expecting from a spectroscopic alert, right? So how do you see synergies coming in for these like type of facilities that I mean, both are issuing alerts and receiving alerts, like maybe at a certain point, but yeah.
Yes, so this is why I think this is the time to be thinking about synergies. We don't really have a spectroscopic survey at the time, so I don't really, I cannot foresee how this could work. What I would assume is that as the same way we have the brokers for CTF, we will need to have a broker for spectra. If at some point we have a spectroscopic survey, any type of spectroscopic survey that just scans the sky and takes spectra of anything that changes, let's say. So I guess we will need to have its own brokers, and then we will need to cross-match coordinates. And at, I guess at the beginning, do a lot of eyeballing and human work until we figure out how to uh, uh, automatize everything.
Right, because I think we don't have that much idea about the spectroscopic alerts in general, right? Like we don't know how they look like. We don't
Right,
have
because
technologies like
we
this, so
never
it's
had
very
one.
rich.
So
Yeah,
yeah, we
right.
never
Yeah, like
had
we never
one.
had one, so we don't know what to expect.
Yeah,
But yeah, like that's
yeah,
exciting and yeah, like something to really look forward to. So yeah, I
yeah.
think this is great. I think this is a real like example of like yeah, like where the values of a big spectroscopic facility that do like time resolve the spectra can yeah can be like motivated, etc. So yeah, like anyone else having questions? No? Okay. If no, then I think we can close the session here. And thank you again for this great, fantastic talk. And yeah, I think like see you pretty soon at LSST TVS colloquium.
Thank you very much, Priscila.
Thank you.
Yeah, see you
Bye
around.
bye.
Take care.
Bye.
Ciao.
Bye.